Hello, hello. Welcome to the Kafka Meetup. And my name is Guo Zhang. I'm a committer of the Apache Kafka project and an engineer at Confluent. So for those of you who are first to this event, the Kafka Meetup is driven by our community to have a venue for folks to come and share what you have done or what challenges you have been facing technically, or what crazy exciting ideas you have been brainstorming, both in the Kafka internals and also in the ecosystems, and more generally in this new real-time streaming world as well. And I think at the moment we have more than 150 Kafka meetup groups across the globe. So if you are not local to the Bay Area, San Francisco area, you're traveling for the summit, I would highly recommend you to go to our Apache Kafka official website after this event to look for the Kafka meetup group that is closest to you for future events. And so today is our first Bay Area event hosted by Confluent, actually the first time in our San Francisco office. We are very excited to share with you folks about the projects that we are working on and the challenges or the problems that we're trying to tackle, along with two other our friends from the Apache Kafka community from Bloomberg and Airbnb. And one last note, so next month in November, we'll have our fourth event in our new Mountain View office at Confluent. So stay tuned. Okay, without further ado, let me introduce you to Frank, who is going to talk about how we build our cloud.
Thank you, thank you. Is anybody here a Brewers fan or a Nationals fan? All right, the Brewers are in the wild card game right now, and we're up 3-1 in the top of the sixth. So I'll be looking at speaker notes and the score while I'm doing this presentation. Okay, cool. I am Frank, and I have been with Confluent for a little over a year, and I am on one of the cloud teams. I used to be on the cloud team back when I started, and then it has become it has scaled immensely and has broken up into now many teams, so I just say I'm on one of the cloud teams now. But you guys are in for a treat today because I am going to be talking about more than I think has been talked publicly about the internals of Confluent Cloud from an engineering standpoint, and I'll try not to talk about too much so that I can come to work tomorrow. So we'll see, yeah, I'll try to walk that line. So, well, first, what is Confluent Cloud? For those of you who don't know, there's been a lot. Hopefully you heard about it in the summit, but it's the best Kafka as a service and Confluent as a service platform out there. We run Kafka as a service and KSQL and Connect and Schema Registry and everything that we provide as a company, self-service, fully managed, and serverless. So we first started probably 3 years ago or 3.5 years ago. And it was just a very simple, throw everyone in a room, get bootstrap cloud. And it's amazing to see what we've grown into. Currently, animation on this one. So currently we're in 3 clouds. We're in GCP, AWS, and Azure. Azure is very new. And we're over 29 regions, and we host over 2,500 brokers in total. And so yeah, so that's the scale that we're currently at. I wish I had taken the time to make the graph of how it's gone over time, because actually I don't know how it's how that line looks. But we started with 1, 1, and probably 6 or 8, and now we're to these numbers, which is crazy to think about. And so yeah, so we're going to talk about the internals of cloud. And when you have a cloud product or any PaaS or software as a service thing, you primarily have 2 main parts. You have the data plane and you have the control plane. And the control plane is how everything communicates with each other to handle provisioning flows and feedback loops for self-healing, and handles your APIs for creating stuff. And the data plane is how you actually access stuff. So for Confluent Cloud, it's connecting to the brokers, and doing the actual thing that you are paying money for, and the control plane would be all right, now I need to create my clusters, and you expect that cluster to be working and self-heal and scale and do all this stuff. So, so we're going to start by talking about those 2 things And so, yeah, so I'm going to start by giving an architecture or a high-level architecture of how we handle just cloud in general. So we are across 3 clouds, as I said. We're across Azure, GCP, and AWS. And we think about it logically as having 2 concepts. One is the mothership, and then one is the satellites. And unfortunately, those terms predate me, so I don't know where those are from. I'm not a Star Wars guy. I don't know if that's a Star Wars term, but it seems something space-like. But basically, we have the mothership, which is we host in AWS, and then we talk to these satellites. And the satellites are where the brokers are deployed, and it's where your Kafka clusters are running. And they communicate with each other over Kafka. Of course, what company would we be if we did not use Kafka for Confluent Cloud? And this is how the mothership communicates asynchronously to the satellites, and this is how it sends data. And we'll talk about a little bit later, like what that data is and what is actually sent over this Kafka bus. You can think of the satellite as a logical unit that has different components, and if we need to add Kafka clusters or scale to a new region or a new cloud or whatnot, you can think of it logically as like, we'll add satellites. And so let's take a look at what these satellites look like. So every satellite is a Kubernetes cluster. Surprise, Confluent Cloud uses Kubernetes. What doesn't these days? But every Kubernetes cluster we'll use to host one-to-many Kafka clusters. And there really is no, the number of Kafka clusters or brokers that we run on any given Kubernetes cluster is arbitrary in the sense where we just want to like limit the blast radius if something horrible were to happen. And we'll actually get into reasons later like how this has like saved us. But yeah, so this is how it looks. We'll have our Kafka clusters, which we use the Kubernetes, I think it's called the operator pattern these days. I worked with operators way back when it was first a thing, and I don't even think it was operators at the time. It was just third-party resources and then CRDs. And we'll talk about this abstraction in a little bit. But basically, every satellite is a Kubernetes cluster, and it's fairly easy to deploy a new satellite. And we run all of the Kafka clusters in there. And then on the bottom left, that's just meant to represent different services that we run alongside to facilitate stuff that happens in the cluster. So for example, if we go on the bottom right, which is the mothership, if you remember, if you go to the UI and you say, create me a Kafka cluster, that'll call a bunch of like internal APIs, you know, like post Kafka cluster or whatever. They'll persist some state in our database, write some stuff to Kafka. It will be routed to the satellite of your choice. So like if you wanted a Kafka cluster in AWS and US West 2 or something like that, the appropriate satellite would receive that message. And then we'll have what we call our a sync service that's basically listening, and it will go ahead and create our operator abstraction. And then we will have an operator that implements all of the lifecycle or feedback loops. So your common operator pattern where you have some custom resource and you create custom resources, and then you have some operator that's listening on changes for those resources. And I could give a whole other talk on like Kubernetes and operators, or you can just talk to me after if you want to know more about those. But we'll talk next about what's actually sent over these. What you should get out of this diagram is that logically there's the mothership in the bottom right, and then we have our satellites, and it's fairly easy to spin up satellites. And this actually makes it easy for us to bootstrap our product into new clouds. So I should say relatively easy with emphasis on relative. So when we, for example, expanded into Azure, we didn't need to rewrite a bunch of stuff. We just extended this concept and just tied the hooks into whatever we needed to do to make these Kubernetes clusters run on Azure. The other thing I'll mention here is that we kind of like pick and choose what we use Kubernetes for. So for example, like vanilla Kubernetes is you just have these pods and you allow them to be deployed on, like you don't care what node they're deployed on, you just let Kubernetes figure out the best place to place these pods. We do that for some stuff, but for example, with brokers, we maintain a one-to-one relationship between a broker and an instance. And so we'll like make sure that is true by using like tolerations and affinities and stuff like that. But what Kubernetes is really good at is its own control plane. So this concept of declarative, like declaratively defining what you want and then having Kubernetes in an eventually consistent way, like make that so. We went back and forth with like, do we write it ourselves? Do we use something that already exists? And Kubernetes actually handles this part very well, with some caveats that we'll talk about later. Okay, so like what sent over this Kafka bus? One of the things we did like good early on is we like defined a good abstraction that has actually lasted us pretty well, even through today. And pay attention to the bottom. So like on the bottom, there's like the rocket ship, or like mothership, satellite. Just so like you can follow along like where this stuff mutates. So when you create something, let's just say a Kafka cluster, it will generate what we call a PSC, or a physical stateful cluster. And that's the name of the CRD. So if you're familiar with Kubernetes operators, that is the name of the custom resource that we use. And so you create this PSC, or this PSC gets created, and it basically fills in information that is common to everything. And to help you understand it, when Confluent Cloud first started, it was just Kafka. But now we have KSQL, and we have connectors, and we have schema registry. So this slide actually holds for all of the CP products that we host in the cloud. So initially it was just Kafka, but when you create a connector, when you create a KSQL, when you create, or when you use schema registry, this concept is also true. So the mothership service, or basically the microservice that fields the request from the UI, will basically fill in the bare minimum that it needs, and then it will shoot it off to another set of services that live in the mothership, and we call them like our cluster spec services. But the importance here is that we have one per CP product. So we'll have like a Kafka specification service and a KSQL specification service. And we'll basically pass them this object over gRPC, and then they'll fill in what they want to fill in, and then they'll pass it back to us. And this is important because me on the cloud team, like I know how to build cloud. I think I know how to build cloud. We're getting better at it every day, but I'm not good at like running Kafka. The Kafka team is the best at running Kafka, and our KSQL team is the best at running KSQL. And so we'll pass them this object, and we'll let them iterate on this microservice and manage this microservice and basically fill in the bits that they need. So we'll pass them this abstraction, and we'll say, someone's requested that something gets deployed. Here's some parameters to help you make decisions, or some flags or whatnot, and then they'll fill in the rest. And then they'll pass it back to us, and then this is what we will send over Kafka to the appropriate satellite. And then this will get created via the Kubernetes custom resource, physical stateful cluster.create if you're using the Kubernetes generated clients. And then this will manifest itself into all of the Kubernetes resources that the operator implements. So there might be some services, some pods, there's a stateful set in there, volumes, there's other stuff as well, but that happens in the satellite. So the rightmost side of this will look familiar if you're familiar with Kubernetes. And I touched on this a little bit, but the different color people basically like represent different teams. So it's a different team that manages each like vertical representation of this, which is something that has been really helpful now, because then as we scale now, it's really easy for this to be like decoupled, so like different teams can work on different things. Because when cloud first bootstrapped, or when we first bootstrapped the cloud, doesn't necessarily matter how decoupled it is, because I can just turn to the person next to me and say like, hey, I'm gonna make this breaking change, like just like make your change, and they'll be like, okay, and they'll do it. But this abstraction really helps because it's like the contract as we send it like through our platform, and different teams can work on it independently. Okay, so let's not talk about the data plane. So let's now talk about the data plane. Pull up some notes that I may have for these slides. The data plane, the data plane is what needs to be solid. Like the control plane, like obviously should be solid, but if you have a bug in your control plane, or or like you're not able to create clusters, like that's definitely not okay. But if your data plane is working, like that's like if you had to pick one of the two for it to like never go down, like it's your data plane, because that's what you don't want the connection. You still want to be able to produce and consume. And so this needs to be solid. And so how this works is this represents brokers, and this represents a Kafka cluster. And I'm going to like step outside of the logical abstraction of Kubernetes and just talk about it from just from a pure like broker point of view. So let's say we have a cluster of, I guess I have 4 brokers here. And the way we'll do it is we will have a load balancer, a layer 4 load balancer that fronts every single one of those brokers. And so like depending on what cloud you're in, you'll just pick the broker or the load balancer technology for the cloud that you're in. And then each one of these brokers will get a DNS name. If you use Confluent Cloud and have introspected like the logs, you'll actually see these names. They're a little bit longer than this. This is just like the prefix of the name. But it's basically like B and then the ID of the broker and then the PKC, which is actually, so there's, in Kubernetes land, there's your custom resource definition and then there's your custom resources. When you create one, you give it a name. So for Kafka, it's physical Kafka cluster. For KSQL, it's physical KSQL cluster. And its physical stateful cluster is the custom resource name. So in this case, it's Kafka, so physical Kafka cluster. And then, so with just this, it would work fine. But we don't want to hand you, like, Confluent Cloud is serverless, so like you don't know anything about the brokers. So let's say we had a 100 broker cluster. You don't know there's 100 brokers. You just care about the throughput that you provisioned and the storage that you want. And so I don't want to hand you a list of like 100 DNS names and I'd say like put this in your bootstrap.servers. And then like a week later, I'm like, oh, by the way, now it's 102 brokers. So like add these 2 to your thing. And so what we do to get around that is we deploy a special layer 4 load balancer. And this is what we give you for your, this is what we tell you to put in your bootstrap.servers. And under the hood, basically what this does is we'll use, this will point to a healthy broker. And we basically leverage the cloud or the load balancer health checks. And then to basically let us know if like what broker is healthy, and then this will facilitate like your initial request, and then like the metadata API will give you back the DNS names for all of the brokers in that cluster. This caused some issues early on that we'll talk about later on how changes we had to make to Kafka to make this work. But this is essentially data plane. Now notice like it's simple, and like one thing that we learned is that it's like sometimes it's cool to have really complex architectures and be like, I have all these moving parts and it just all works seamlessly, or at least you think it works seamlessly. But sometimes it's just nice to have like a boring system that works. And for the data plane, like that's definitely what you want, especially if you're paying us money for it. So that's the data plane. And then like, so for example, I'll say one more thing. We offer products like VPC peering and stuff, and that doesn't change the data plane. It just changes whether these things are public or private and where they're accessible from. So like I just said, there's some changes. So I guess I'll start by saying like before Confluent Cloud, if you think about like the team at Confluent that's working on Kafka, you know, someone will say, so someone pays us for support and they're like, we have a bug. And we'll be like, okay, and then like we'll ask them for logs maybe, or we'll ask them like what happened, and then there'll probably be some dialogue where it's like, we'll try to reproduce it, we'll ask them clarifying questions, they'll give us more data, and then if we're lucky, maybe we'll reproduce it, maybe we'll have a bug fix, we'll come out with a release, and then they'll deploy it. If it's like a security bug, maybe that loop will be a little bit faster. But with like earlier on, we talked about the scale we're at, and if we're running 2,500 brokers and we're running like a pretty significant Kafka installation, we're going to be one of those customers, and we're going to find a bunch of stuff potentially that's wrong. And so what we noticed along the way is we needed to make changes to Kafka itself to make it more cloud native and to work better in the cloud. And so this slide basically demonstrates what I just talked about. Is there's this cycle like report, reproduce, fix, release, deploy. And sometimes this would take months or never happen, because let's say like you got all the way to release. Like sometimes depending on how a company deploys Kafka or manages it, sometimes it may be too risky for them to deploy, so they'll like deal with the bug fix because if they like update or roll or upgrade their Kafka cluster, like maybe there's just too much risk there. And so what we quickly found is that like if you are using Confluent Cloud, or like before Confluent Cloud, I guess, this cycle was very slow. And by slow, I mean like months to never, maybe, like depending on the caveat I just talked about. But with cloud, we're able to iterate extremely quickly to like sometimes hours, but like days. And I say hours if it's like a security thing and like we have to like move quickly. And this is awesome because it's allowed us to become very good at running Kafka because we're able to catch a lot more things and solve them a lot more quickly. Pull up my notes again. So, okay, so now we're going to do a fast fire on some of the changes we made to Kafka to make it more cloud native. And I know cloud native is an overloaded term. You can think of like cloud first, I guess. And actually, I should mention something about cloud first is that when we say cloud first, what we mean is that if we have a new bug fix or a new feature or something, we'll test it in cloud first before we ever release it to like CP or like our Confluent platform, which has allowed us to like test it a lot more, which ultimately resolves in better Kafka in general. But okay, so this list is by no means exhaustive, but it highlights some of the cool stuff. So before cloud native Kafka, certificate renewal requires broker restart. And this is because you have to, like in Kubernetes land, you can think of like we store the certificates in like a Kubernetes secret and they'll update the secret. And then Kubernetes will make sure that that secret gets remounted in the pod, but it actually is going to take a broker restart for it to pick up that new cert. And to be honest, like this is completely okay when you're at a certain scale. Like if we have like 100 Kafka clusters, like expires every how many days, 60, 90, whatever you have it set to. And then you'll like, have some person who is on call that week that like rolls all the clusters. And this is fine up until a certain point. But when you like go like an order of magnitude greater than that, like you quickly start to see like, this is not scalable. And not only is it scalable, because I guess you could always hire more people to do like to renew the certs, but it opens yourself up to issues along the way that you could potentially run into. And so now with cloud native Kafka, certificate renewal doesn't require a broker restart. And so we're able to basically renew certificates for our clusters without having to restart all of the brokers. And we're able to restart brokers in a way that is seamless to the client, but this reduces so much complexity and potentially takes away all like potential issues. And so this is one thing that we did. The other thing we did is we made it multi-tenant. So we quickly found out that like, if we're going to create an actual physical Kafka cluster for every single person that like says create cluster in the UI, like this is going to become very pricey. And so before Confluent Cloud or before cloud native Kafka, it was one cluster, one tenant. With Confluent Cloud, it's one cluster, many tenants. So we basically have multi-tenancy in the cloud. We have like product lines within Confluent Cloud where you can still have one cluster, one tenant, if you so need, because like if your use case requires it, we do offer that as a product. But for our normal use case, when you go into Confluent and you say, give me a Kafka cluster, we'll utilize multi-tenancy. And now like these are some bug fixes that we quickly noticed. So Kafka used to ignore multiple values in DNS records. So when you create a DNS record, you can have multiple values and multiple like IPs. And it would ignore, like before Confluent Cloud or before Cloud Native Kafka, it would only use the first one. With Cloud Native Kafka, we actually utilize all of them, which really helps for fault tolerance because if your client, if you've architected your system in a way where you're gonna rely on that fault tolerance in the DNS record, but your client doesn't actually do that, then you're not actually getting the fault tolerance you want. And so this is a bug that we found and we're able to fix it in Cloud Native Kafka. Another one is clients resolve broker names once. So with like clients, when they make their connection, they'll make the metadata request, they'll resolve the brokers, and they'll just always use those IPs. But with Cloud Native Kafka, if you get certain failures, the clients will re-resolve the broker names, which is very important for cloud because we do like move stuff around like underneath the DNS names, and so it's very important that this occurs. All right, so before Cloud Native Kafka. There's native quota policies. And I believe we even have like a quota framework that you can use to like create your own policies. With Cloud Native Kafka, we've implemented some policies that supports multi-tenancy and then also will throttle based on load. When you have a multi-tenant system, you have to put some of these checks in place so that one tenant can't like DDoS the other tenant, other tenants in the cluster. And so this is something that is in the Kafka that we run in the cloud. And so before we move on to lesson learned, like what we can see is that running cloud has taught us lots of things in it, and it has influenced the way in which we implement Kafka to the point where we actually created a dedicated team that makes changes to Kafka specific for the version of Kafka that we run in the cloud to give you the best Kafka as a service available. Now, when we like building a cloud, like if I've learned anything, it's that like doing this stuff is extremely hard. And we've learned like tons and tons and tons of lessons. I'm gonna touch on like a few lessons that we learned, or at least I learned. These are the most important from my point of view. If you were to poll all the people on the cloud team, you would probably get 100 different answers. But we'll just touch on a few. One is that you should think about your API story early. And like if I knew the perfect time to think about your API, I would say do it when you see this. I still don't know what that perfect time is. When you're one small, like lots of projects like this, whether you're building a cloud or like your leadership has said like, build this thing that's gonna be like important to our business. Like you might cherry pick a team, throw them in a room and say like, you're not leaving this room until you like do this, right? And so you don't have to worry about some things because everybody there is sitting right next to you, and the most important thing is getting the feature out the door. And certain things aren't as important that will like become important later on. And so for example, things like making an API contract that has a good versioning strategy and having good backwards compatibility guarantees or whatnot are extremely, extremely important when you have hundreds of like engineers working on it across multiple teams. And one lesson we learned is that we should have thought of it earlier, right? Like there came a point when cloud split up into multiple teams, and we weren't just one team anymore, where it was easy to make these changes and not necessarily have the guarantees because we were all a closely knit group. But then as we split up, it quickly became apparent that we have to have these guarantees and these contracts in place to improve the developer experience when these teams are developing. This next one is fun. Okay, so before my time at Confluent, I dealt a lot with Kubernetes. And actually, like, we have like a template for like our slides, and I randomly chose like this one, and like it's blue, but it wasn't because of Kubernetes. It was just random that like Kubernetes landed on this blue. But so I'm going to tell a story about a bug that we found in Kubernetes. So it's very easy when you use something like Kubernetes to think that it's just like gonna work, and it does. Like 99.9% of the time it works, and Kubernetes is one of the best projects that I've ever seen when it comes to testing and like their review process, even painfully so. Like I've spent months getting something reviewed, like a little thing, but it results in a very solid product. But we use the cloud providers. So for example, early when I said we create a load balancer per broker, we'll use a Kubernetes service of type of load balancer. I can talk more about that later if you want, but that's not important to this. But basically, Kubernetes provides the ability for different cloud providers to implement an interface that basically has that implements certain things. So for example, if you have a Kubernetes service and you set it to type load balancer, that'll mean different things depending on what cloud you're in. Simple enough. So there was a bug in Kubernetes where every time you modified a Kubernetes service, it would delete all of the listeners off your load balancer and recreate them. And this is specific to the AWS provider. And so what that means is if we updated our operator and we said, add this annotation, like a foobar annotation, and we then deploy that operator. And let's say we deployed it a region at a time. So let's say we deployed it to US East 1. What Kubernetes would do with this bug is it would say, all right, here's all the listeners on all of your load balancers. I'm gonna delete them all and then recreate them. Which like is like, if you were running a small scale application, you wouldn't even notice it because it happens so quickly. But if anybody runs AWS, you know you run into rate limit issues. And so what happens is then the moment you run into that rate limit issue, everything stops, and now you're going to have noticeable time when you don't have your load balancer on your broker anymore and you can't connect to it. Yeah, and so basically, like, we identified this bug, and this has actually allowed us a platform to contribute back to Kubernetes to help make it better. But this is actually another one of those things that you only really run into when you run something at a certain scale. But what this has taught us is that we can't just like take Kubernetes at face value and use it. We have to have strategies to mitigate potential bugs that may exist. And if we identify a bug, we need to have a path to fix it. And actually, Kubernetes is extremely good at, once there's a fix, getting it in the next release, and then you can hotfix releases. The challenging part is then, like, once Kubernetes does cut the release, you need to have a path to make sure that all of your satellites, like we talked about earlier, are upgraded. So yeah, that was a fun one. Some other ones: hardening your testing frameworks before onboarding engineering. When you're one team, it's really easy just to test stuff, right? Because maybe you have some like manual installation of like a local environment running, and like you can test your stuff on there. As you scale, though, it doesn't really work. And so you need a way for developers to seamlessly test stuff end to end. Unit tests, integration tests, and end-to-end tests. And it needs to just work seamlessly. Because like, it may be possible for them to do it, but sometimes I think it's very easy to overlook like the developer experience with developers. Like, when a developer works on something, they should be like leave work feeling satisfied that they like accomplished something. And it's very hard for them to do that when they spent 90% of their day trying to get the tool to work that they're running their stuff on. And so it's very easy, or a takeaway is like harden your testing frameworks before onboarding a larger audience to work in your cloud. This one is build good abstractions. This is kind of like a joke because like sometimes it's like hard to figure out what the good abstractions are like before you mature to a certain point. It just turns out that like we created a good abstraction from the beginning. It will go through refactors as time goes on, but it has lasted us like 3+ years. And we've added to it and refactored it a little bit, but actually Kubernetes really like helped us create this pattern because they encourage abstractions like this. And then walk the line between automation and manual tasks. When you're trying to bootstrap something to get it out the door, you don't have time to automate everything. We all know like you should automate everything, but you're gonna automate some stuff, but some stuff you're gonna say like, we're just gonna like do this manually. But like if you choose to do something manually and then it turns out like, oh, like this is used a lot more than we thought or whatnot, like recognize it right away and then automate it right away so that like a year down the road, it doesn't take up 50% of an SRE's time doing the manual tasks because you didn't automate it earlier. The other one is the cloud isn't free. So like one of the big things with the cloud is you don't have to pay for physical hardware. You can just use what you pay for, right? So like if you use an instance, use it and then tear it down. Well, it turns out when you like build clouds or like build stuff at scale, like cost becomes extremely important, which I mean, obviously like network is extremely expensive just because it's easy to do something. So like maybe for example, say it's very easy for you to use the same instance type because of the way you implement your infrastructure, for example. Well, if you're running an application on an instance that costs like maybe it only needs like 100 millicores of CPU and you're giving it like 4 CPUs, sure, it may be easy from a development and like ops point of view, but if it's costing you through the roof, like it makes sense potentially to like go back and like refactor so that you can save yourself a lot of money, especially on like the networking side, because networking is probably like the biggest cost of any of most projects that run in the cloud. Cool. So that was a brief overview of the cloud, and hopefully went into a little bit more detail than you've heard before. I think we have a few minutes for questions. I'll be here all night, so you can ask me questions, but I think I have time to take a couple of questions if we're set up for questions.
Any questions?
Yeah, just with the multi-tenanted clusters, does that introduce additional constraints? So say you had 2 tenants requested a cluster, those clusters got mapped to one physical cluster, and they tried to create topic A, both of them. would they be able to do that, or would one?
Yeah, so
be
the whole
able
thing
to?
with like multi-tenancy is like making it so that that is possible.
Okay.
When you're in the console and you create a Kafka cluster, you think you're getting a cluster, and you are. You are getting your own logical Kafka cluster. Yeah, it would basically it wouldn't be multi-tenancy if you created a topic and you're like, no, someone else already has a topic name, and you're like, well, what do you mean? Like, I don't have a topic by that name. But yeah, we basically made it so you're able to do that. Come on, it's your guys' time. You can ask anything about Confluent Cloud.
You mentioned the cost isn't free, or the cloud isn't free. So
Yeah.
what are some of the strategies you had to minimize costs for like data movement? So I think that's something that's kind of not recognized.
Yeah, so like, for example, like cross-zone traffic, you need to care about cross-zone traffic. Like sometimes it's easy just to like not think about it and be like, if it cross zones, cross zones. But it's very important to say like, or it's very important to think about like where traffic crosses zones to make sure you cross it like on certain cost boundaries. But then other things like instance type. So for example, we have that PSC abstraction, and it's very easy for us to like just use the same instance type. But like maybe schema registry doesn't need the same instance type as Kafka does. And like before you know it, like that cost can like add up, and it's like, well, maybe we need to revisit like the type of instance type that like this product needs. So those are the two things.
How does your upgrade, not the upgrade, the version and upgrade the whole deal? Do we get to choose the version and stay in the same version in the cloud, or how?
Yeah. So actually, I didn't really talk about like, so we call them roles. Maybe they're called upgrade. So the whole thing with Confluent, as you saw today in the keynote, is it's like serverless. Like you don't care about broker versions. You don't care about anything. Like the things you care about will expose to you. So like if it's a topic level configuration, we'll expose that to you. But things like broker version, like we remove the stress for you to figure that out. We'll always run like a very up-to-date version of Kafka, more up-to-date than you'll find like in like a Confluent platform, for example. And yeah, and like we'll seamlessly, so for example, like if you have an application and it's running and like say you're producing like multiple times a second, or like you're doing like a gigasecond or something, let's say a big application, we're able to basically upgrade your cluster, renew the cert, like update configuration without like your application like ever noticing. But yeah, that was basically a long answer. But yeah, you don't have to worry about those details.
Any upgrade problems with Kubernetes you have run into? Or?
Yeah. So Kubernetes. So if you've ever worked with Kubernetes, like Kubernetes alpha, like really means production, really means like stable, right? Like, as you move through Kubernetes versions, it's very good. But like, for example, like 6 to 7 was painful. It was either 6 to 7 or 7 to 8. And then like from etcd, like 2 to 3 is painful. So there's certain things that like require a little more like manual touch and like oversight to just make sure it happens seamlessly. But everything from the Kafka side is pretty seamless. And that's nothing that cloud, I mean, that's props to Kafka for making it so backwards compatible and everything. I think there was a question up here. Oh, he was right, it's Mike.
One thing that struck me was on your early slides, you used Kafka as the backbone for communicating with the mothership to all the different clouds. Mm-hmm. That struck me. It was and it made perfect sense once I saw it, but it surprised me.
Yeah.
And then I also noticed you used the word, you said microservices. So it seems like the basic things that made Kafka popular, you're using directly in your control plane. Is that?
Yeah. Yeah, actually my team is like creates a lot of like the microservice applications that like use to like build the cloud. And like, I only really talked about one flow of communication, like from the mothership to the satellites, but there's an additional flow of communication from the satellites to the mothership that like communicates status, right? So we can do like our self-healing. Like the clusters will tell us like the state that they're in and like if they need to be, healed, quote unquote. And like Kubernetes helps with self-healing because of just what Kubernetes is. And then we help with that with more stuff on the Kafka side, but.
Can you repeat the question?
I think I can answer this. Yeah. Do we use managed Kubernetes? So in GCP, yeah, like we use GKE. In AWS, we used to roll we didn't use, what is it, EKS. We used one of the many bootstrappers there is, COPS. And then I think we're going to use EKS eventually. But right now, I think there's like some limitations with like the availability that it's in, or I forgot. I'd have to ask the team that's responsible for Kubernetes. And then in Azure, we use whatever it is in Azure, AKS, yeah. So, and that's like, it's a blessing and a curse, right? Because you're like, because then what I mentioned earlier about finding bugs in Kubernetes and fixing it, like if there's a bug, like GKE manages the version for you. Now, like GKE is very good about coming out with new ones, but then, yeah, and that's why like we behind the scenes like mitigate stuff. Like we have to put things in place to make sure that we mitigate this stuff, which is like, it's a trade-off. It's like you can use the hosted one and then like build mitigations to make sure that it's up to your standards, or you can like not build the mitigations and but like roll your own. So it's a balance that we play. But we found that in general, like leveraging stuff that we can like ends up working out for us. Plus it's like sometimes cheaper, I think too, if you like, sometimes not. But I'll be here all night too, so if anybody has questions that they don't want to ask me now, you can ask me later.
Okay, any more questions? Well, I'd like to thank my colleague Frank again. Thank you.